Hello everyone, my name is Nicolas Trangez and I work at Scality as a principal architect. And today I'll talk about Scality's experiences with Kubernetes, what we learned while starting to run and use Kubernetes, and the future where we see Kubernetes heading, where we will use Kubernetes as part of the Scality product offering. First, a little bit of history. Scality builds a product we call Ring, which is a storage product for file or object storage. It's been around for quite a while, and it's a software-defined system, which means that Scality provides software as packages, system packages. You provide the operating system, the server is the operating system. We install, and you can run the storage solution. We've been using RPM, the standard Red Hat packaging system, since forever. And we're using a system called SaltStack to automatically deploy Ring on your servers. Now, over time, the cost and the effort we have to put in packaging all our software has been going up. We are adding more dependencies to our system, which means more packages. We still have to support what I'd call ancient operating systems. Think Red Hat 6 in 2020, which is becoming quite complicated. And we've often run into our packages conflicting with packages that may be installed on the servers by our customers. Furthermore, we started using so-called modern technologies, think Golang, think Node.js, where packaging using the RPMs is somewhat difficult because you easily introduce a lot of dependencies in your application. A couple of years ago, we started a new project. It's called Scality S3C, the S3 connector, which was is mainly developed using Node.js. As said before, environments like Node, which easily bring a lot of dependencies, are fairly difficult to package for RPM as native Red Hat packages. So we decided to move to Docker, where we use Docker-style containers as a way to provide all the software, including all the dependencies, to our customers' systems, which decouples the services that comprise S3C from the host OS. Now, in deployment, S3C is deployed fairly statically, as if they are system services. We deploy a couple of instances of one particular service, one particular container on one node, some others on another node, etc. at install time, and then we simply run those containers to provide the storage service. In 2018, we started a new project called ZENKO, which is a multi-cloud data controller. And we took the learnings from S3C and also some software that is packaged as part of S3C. But ZENKO is more built for the cloud. It's supposed to run in cloud environments, but also on premises. It's container-based. It actually shares a lot of containers with the S3C service, and it's using a so-called microservice architecture. Because of all of this, we decided to embrace Kubernetes, which, despite what some vendors or analysts are saying, does bring some kind of portability between cloud environments, multiple cloud environments, and your on-premises system in your data center. And it gives more flexibility. So where S3C is deployed, as I said, in a somewhat static way, Kubernetes really allows you to easily scale up a number of services, to move services from one host to another, etc., etc. So this means back in 2017, 2018, we really started to invest a lot in Kubernetes and build a lot of knowledge within the engineering team, the technical services team, when it comes to Kubernetes, how to operate it, how to install it. So here's a couple of experiences and learnings. So what is Kubernetes? Most of you, everyone has heard about it and has a notion of what it is. I think we can look at Kubernetes as an operating system for a cluster. It's a somewhat popular definition. It's not technically entirely right, but bear with me. It's basically something that allows you, just like an operating system, to run processes, to run so-called pods. You can compare those with containers. It's not entirely the same thing, but still across a number of nodes that make up your cluster. So Kubernetes is responsible to schedule pods on particular nodes. Similar to an operating system, it will manage access to scarce resources that are local to a node. For example, CPU and memory. You may want to limit the amount of CPU a particular service or a particular instance of a service can use, the amount of memory one can use, etc. Next to that, access to local devices, think GPUs, think TPUs, and whatever new hardware is coming up, and local storage, where with local storage, I simply mean disks that sit in a server. Then also Kubernetes, similar to an operating system, think your Linux kernel, is responsible to set up access to the outside world, which means the network using a so-called CNI plugin, and to storage using a so-called CSI plugin. The architecture of Kubernetes, and here I start with something that may be a bit controversial. I think it's fairly simple because it is very consistent and regular. In general, if you look at Kubernetes from a super high level, it is a declarative model of how you want to deploy your storage. And the declarative model, the objects, are stored in a highly available database called etcd. Then once you declare how things should work, there are so-called controller loops, which look at what is in the database and refine these objects into lower level objects. An example there, for those who are aware of Kubernetes and its objects model, is you have something called a deployment, where you say, I want to run this number of instances of a particular container in my cluster. The deployment controller loop will then refine that into a so-called replica set, which is another virtual object. It's not something that runs on a system somewhere. And then finally, a replica set will ensure that the desired number of pods will be scheduled across will be created again, sorry, in the data store. And eventually these pods will be running on the actual servers. There's a couple of host services, Kubelet and kubeproxy, which will make sure that containers are scheduled on the applicable hosts by talking to so-called CRI implementation, which is the container the container runtime implementation. Think Docker, think Cryo, think Containerd. And kubeproxy will set up a couple of networking services. Overall, we found that Kubernetes has a really solid architecture and a very high-level, high-quality implementation. There are some bugs. There's bugs in all software, so we have run in a couple of them. We worked with the community to fix them. We ran into certain shortcomings of Kubernetes where what's provided doesn't necessarily meet our needs. Luckily, Kubernetes has a really good community, so there's many special interest groups that work on particular parts of the Kubernetes software. You can easily interact with these people, ideally in the real world at KubeCon, but also there's weekly meetings of every SIG where you can raise concerns. You can help writing design documents. You can, of course, contribute code to implement certain things, etc. Now, we decided to use Kubernetes to deploy ZENKO, both in the cloud as well as on premises, but we cannot have Kubernetes as a prerequisite for our customers to have running in their data center. Taking Kubernetes from what is built upstream, the core Kubernetes, to production takes a bit of effort. A plain Kubernetes cluster is really useful for a developer, but it's not ready to run an enterprise-grade storage product in your data center. Things that need to be added, for example, is monitoring, log management, user authentication, a so-called ingress controller to allow outside traffic to go into your cluster and be handled there, network load balancing, the lot. Furthermore, Kubernetes originally was very much cloud-focused, so meant to run in the Google Cloud, the Microsoft Cloud, the Amazon Cloud, where everything is available as a service. Think, for example, I want to have a block device or some other storage device in the cloud. You just say, give me a new block device, and magically it's attached to your virtual machine, which, of course, on premises, we don't necessarily have. Furthermore, we're building a storage product, so we can't really rely on another storage product. So the running Kubernetes on premises poses a couple of challenges, especially for our types of customers. There's, of course, security concerns. There are so-called black sites where we need fully offline delivery. We cannot rely on the internet during installation. There's no disks as a service, so we must support local sites, local drives. Certain customers have their operating system configured in a way that is not alike a VM running in a cloud somewhere where you, for example, use fairly flat networks. We need to make the separation between what is the control plane network, what is the data plane network. Certain customers have really, well, not strange, but more complicated routing rules like policy-based routing, etc., configured on their servers, which potentially conflicts with the way Kubernetes networking works. We need to integrate with existing user directories, think Microsoft Active Directory or an LDAP tree, etc. And for this reason, we built something called Metal Kubernetes, Metalcades. Metalcades itself is a way for us to install a Kubernetes cluster on premises, likely in offline environments on customer services. It's still software defined. We come in, we bring everything you need to run a production grade Kubernetes cluster. And it's mainly using, it's built using SaltStack, which is a Python-based automation framework for bootstrapping phase. And then a little bit of, well, some Go code to implement various services that we need in order to run the cluster. All of this is based on various cloud-native technologies. For example, we integrate Prometheus for monitoring and Grafana for dashboards. We integrate Grafana Labs Loki for log management and many other services.
When you deliver this system as an offline one, and like you said, it's like dark sites and all that, and yes, of course, there are many environments like that. How do you manage it operationally in terms of updates, security, and upgrades in general?
It's split in two parts. We rely on the operating system, including its repositories, to be available. And so if there's a security issue with, say, OpenSSL, then your vendor, in this case Red Hat or CentOS, the community distribution, will provide an upgrade, and you can install it on your servers. For the packages we ship as part of a Metalcades release, we will need to do currently a new Metalcades release, including then the updated packages.
Exactly. I mean, I was more concerned about yours because for the operating systems, you will probably create a path to the internet, but whatever you deploy, is that a seamless upgrade process? How difficult would it be? Do you have to download it separately and then update the entire thing?
Going into technical details, the way we ship this to customers, what the artifact of a Metalcades release is an ISO that contains everything you need to run Metal Kubernetes. There are a couple of RPMs in there, but we try to limit the number of system packages we have to run as much as possible. And then a whole bunch of container images that also need to run inside your cluster. So how to update your system, you will need a new ISO that then contains the new RPMs, or if there are issues with containerized software, the updated container images, and deploy those in your cluster.
Nicolas, I have a question about the storage part. I mean,
yes.
Everything Kubernetes is, usually can move from one node to the other, including, persistent volume. So usually you have a storage layer to manage this part. Actually, with object storage, usually the nodes are pretty static. So, and you don't have, services and stuff moving around. So how did you solve the storage backend in this case?
Good question. Indeed, we cannot, or we are not using attached storage. So all we have is disks that sit in a particular server. We have built some automation to, let me call it, prepare those disks, like check them set up SCSI controllers if need be, format the drives, and then eventually mount them on the system. This does mean that we tie certain workloads that use disks to particular nodes. Now, in the software Scality provides that eventually runs on that Kubernetes cluster, we make sure that there's always high availability, such that even if one node goes down, there are other replicas, for example, of your data, or the data can be reconstructed, etc. So the future. First and foremost, there is a so-called operator pattern you may have heard of in the Kubernetes ecosystem, which basically boils down to codified operations manuals. You declare what you want in the traditional Kubernetes way of working. You give some high-level configuration, for example. And then there is a so-called operator, which takes this high-level description of what you want and somehow turns that into a running system in your cluster. For example, it can manage the software lifecycle, installation, upgrades, downgrades if need be, reconfiguration, extension of your cluster, or even automatic reconfiguration of number of replicas based on load in the system, etc. You can also act on events. For example, if your operator is watching the number of replicas of something, of a stateful application, and one of the instances goes down, the node on which it was running goes down, then your operator could take whatever steps are required to reinstate the number of replicas if it's more complicated than just spawning another replica somewhere else.
I just want to be clear. If I'm doing on-prem deployment of this solution, I need to use your deployment method, or do you guys also facilitate someone that either A, we already have a process that we deploy on-prem Kubernetes clusters and all the constructs? Do you guys also provide kind of here's the prereqs that also need to be in place to also facilitate that deployment?
Very good question, and I was about to answer it in the next slide. So first on operators, from this point on, all the Scality software that is being deployed on Kubernetes clusters, we use the operator pattern to automate all of that. So then, Scality storage for Kubernetes, we are building as well. So to answer the question, indeed, Kubernetes allows us to deploy the Scality solutions in other environments as well, where we are currently working with or looking at, for example, VMware Tanzu and HP Ezmeral. Would it be possible, technically possible, to run Scality software on other types of clusters? Yes, for sure. To which extent that can be supported is, of course, a different question. It needs to be tested. There may be slight variations between all the distributions. So right now, in a first iteration, we will likely require the use of Metalcades on premises unless there's a real need to use your existing clusters or clusters you manage by yourself and spawn up specifically for the Scality software. So I guess the answer to your question is yes, that will be possible. So next to running Scality on Kubernetes and environments, be it in the cloud, be it on premises, there is also providing storage to Kubernetes workloads. There's two technologies out there. One is CSI, I mentioned it before, to provision and attach to file storage, mainly file storage, also block storage, but in the Scality case, file storage. And there is an emerging standard called COSI, which is the Container Object Storage Interface, which is a vendor-neutral way to provision object buckets, etc., with your workload and then expose keys to your applications. So we are involved in the COSI efforts as well, and will likely build a COSI provider for Scality object storage.